So that's the formula of moment of inertia, m1 r1 square, m2 r2 square up to mn r square, n square. This is how we calculate moment of inertia. Okay, fine. Good. After this, we write moment of inertia for a point mass body, for discrete distribution as well as continuous distribution. Fazil, what's the relation of moment of inertia for a continuous distribution? I wrote two formula, I guess, the last class. One is this, m1 r1 square.
Yes.
m2 r2 square and mn r2. Can I use it for continuous distribution? No.
No. Yeah.
This
Yes,
formula.
just m1 r1 square, the first formula.
Okay. So this is for discrete. This formula you will use if your distribution is discrete. Like if masses are spread out, like this one mass, another mass, third mass, masses are spread out throughout the system, then this is discrete distribution. If you have continuous distribution, then you can write your moment of inertia as integral of dm r square. This is moment of inertia. If you have a continuous distribution, then you can write your moment of inertia as integral of dm into r square. That is the formula of moment of inertia for a continuous distribution. Instead of adding, you will integrate it. So this is moment of inertia for a continuous distribution. We did few questions in the last class for discrete distribution. Today we will do questions on continuous distribution. So let's solve first question. So the first question says calculate moment of inertia So there is one axis which is passing through the center of the ring and is perpendicular to the plane of ring. You have to calculate moment of inertia about that. So this is your ring. So this ring is in the XY plane, means this is in the plane of your notebook. And this is the axis. The axis is perpendicular to the plane, means if this is the ring, then this is the axis. Your axis is perpendicular to the plane of the board. So if you draw a ring in this way, the axis is perpendicular to the plane of your notebook. The radius is r. This is dm. This separation is capital R. So you need moment of inertia of the ring about an axis passing through the center. So first of all, you have to decide whether this ring is a discrete distribution or a continuous distribution. The ring is a continuous distribution. There are masses placed back to back over the ring. It's a continuous distribution. So you will write this as, this is integral of its dm r square. You take a small portion of the ring of mass dm. The separation of this small portion from the center of the ring is capital R. So I write it as integral of dm r square. Now you can take this r. R is a constant. Radius of the ring is a constant term. You can take this r outside. So that's r square. It's integral of d. So I'm repeating it again. You take a small portion of the ring and that's dm. The separation of that small portion from the center of the ring is capital R. So the continuous distribution says your moment of inertia is integral of dm r square. Here r is the radius of the ring. It will not change. So I can take this r square outside the integral. I'm just left with dm. Integral of dm means keep on taking small elements throughout the ring and add them. So if you combine all small elements over the length of the ring, then this is r square into it. So the moment of inertia of the ring is mr square. So this is the moment of inertia of the ring, mr square. So the moment of inertia of a ring about an axis perpendicular to the plane of ring and passing through its center is mr square. After this ring, there is another problem of rod. So the next is calculate I take an axis which is passing through the center of the rod. This is the axis about which you are supposed to calculate moment of inertia. This is the origin. I call this as the origin. So this axis divide this rod into two equal parts. The length of the left part is L by 2. The length of the right part is L by 2. If this is the origin x equal to 0, then the coordinate of this point is x is plus L by 2. And the coordinate of this end is x equal to minus L by 2. So this is the rod, this is the system which is given. So rod is not a discrete distribution. So you cannot use addition to calculate moment of inertia. So this is the rod, the length of the rod is capital L. Let's say mass of the rod is m. You're supposed to calculate moment of inertia of this rod about an axis which is passing through the center. And the axis is also perpendicular to the length of the rod. So to calculate moment of inertia in this case, take a small element. A small element of length dx and mass dm. And the separation of this small element from the center of the rod or from the axis is x. So consider a small element, very small element of ring, of rod of mass dm and length dx. So I consider a small element having mass dm and length dx at a separation x. At a separation x, I have considered a very small element. So moment of inertia of rod about axis, you can write this as its integral of dm multiplied by the square of separation between them. The limit is from this point to this point. Means you're integrating this rod from minus L by 2 to plus L by 2. So that's minus of L by 2 to plus L by 2. This is the limit. Okay, can you identify any problem in this limit? This is equation number 1. Is this integral solvable?
No, sir.
Why not?
No, sir.
Why not?
Sir, because dm is the small mass, whereas x is the distance of separation. So we need to
Yes, exactly. Because you have one is x and another is dm. To integrate it, you need a single variable. Either dx with x square, or it would be better if you can replace this dm with dx. So for integration, you need one variable. Either you have dx here or m here. So we'll do one thing. We will try to convert this dm in terms of dx. If you can remember, we did similar thing in center of mass of a rod. We did similar type of calculations while doing center of mass of the rod. Anyways, we will convert this dm in terms of dx. To convert dm in terms of dx, we can use unitary method. So we can write mass of length L is m. Mass of length L of the rod is m. Mass of unit length, it's m by L. Mass of dx length, it's m by L into dx. I'm just using unitary method. For unit length, it's m by L. So for dx length, I just multiply it with dx. And this is what we call dm. So this is your dm, which is m. Equation number 2. Okay, now do one thing. Substitute 2 in 1. Perform the integral and tell me how much is I. Then the expression of moment of inertia will comes out to be its integral minus L by 2 to plus L by 2. It's dm x square. Your dm is m by L dx multiplied by x square. You can take this m by L outside your integral. Yes, no, you are correct. M by L outside the integral and you are left with just minus L by 2 to plus L by 2. It's x square dx. Now you can integrate it easily, right? This is m by L. So if I integrate x square, it comes out to be it's x to the power 2 plus 1 over 2 plus 1. Limit is minus L by 2 to plus L by 2. You can further write this as this is m by L. It's x cube over 3. It's minus L by 2 to plus L by 2. You can take this 3 outside. The moment of inertia is it's m by 3L. It's x cube. Limit is minus L by 2 to plus L by 2. Next, you can substitute limits here. So this I comes out to be it's m by 3L. So this is L by 2 cube minus of minus L by 2 cube. So this I comes out to be it's m by 3L. So it's L cube by 8 minus of minus L cube by 8. So this comes out to be it's m by 3L. It's L cube by 8 plus L cube by 8. So the moment of inertia is m by 3L. It's L cube by 4. See, 1 by 8 plus 1 by 8 is 1 by 4. Now I can cancel this L with this cube. Only square is left. So this is cube and this is L. You can cancel this L with this cube. Square is left. So you have I is ml square by 12. So this is the moment of inertia, which is ml square by 12. So you should remember the moment of inertia of few shapes. The first one is ring. You should know the derivation of ring. The second is rod. Derivation is required. Then you have disc, sphere, and cylinder. You need not know the derivation of those shapes, but you should at least remember the formula of moment of inertia. So the next is moment of inertia of disk about an axis passing through the center and perpendicular to its plane. So you have a disk. Anyway, so this is the disk. The mass of the disk is m. The radius of the disk is r. This is the center of the disk. You need an axis which is passing through the center and perpendicular to the plane of the disk. Means if you draw this disk in your notebook, then the axis is perpendicular to the plane of your notebook. The moment of inertia about this axis is mr square by 2. So this is the moment of inertia of the disk about this axis, mr square by 2. Instead of disk, if you have a hollow sphere, moment of inertia, not hollow sphere, cylinder, of hollow cylinder about an axis passing through its center. So this is your cylinder. You have an axis which is passing through the center of the cylinder. This is the axis which is passing through the center of cylinder. So the moment of inertia, the radius of the cylinder is r, the mass of the cylinder is m. If the cylinder is hollow, then the expression of moment of inertia is same as that of ring. You need not derive these results. You should know the derivation of ring and rod only. So if you have a hollow cylinder, the moment of inertia is same as that of a ring. So instead of hollow cylinder, if I have a solid cylinder, instead of hollow cylinder, if I take a solid cylinder, then for the solid cylinder, it comes out to be mr squared by 2. So the moment of inertia of hollow cylinder matched with that of ring, but that of a solid cylinder matched with that of disc. Then you have hollow sphere. Hollow sphere. About axis passing through its center. So if you have a hollow cylinder and I take an axis which is passing through the center of the cylinder, this axis. The radius of sphere is r and the mass of the sphere is m. The moment of inertia about this hollow sphere is 2 by 3 mr square. But instead of hollow sphere, if you have a solid sphere, so if you have a solid sphere, this is your solid sphere. And this is the axis which is passing through the center. Then for solid sphere, your moment of inertia comes out to be, it's 2 by 5 mr square. So now, can you tell me which will rotate easily, the hollow sphere or the solid sphere? Which one will rotate easily, the hollow one or the solid? Which sphere will rotate easily, the hollow one or the solid one?
Hollow one.
Hollow one. The sphere which have lesser moment of inertia will rotate easily. So which one have lesser moment of inertia?
The solid one.
Solid have the smaller moment of inertia. So the one having smaller moment of inertia will offer smaller resistance and will rotate easily. See, this 2 by 3 and 2 by 5. 2 by 5 is smaller. So the sphere having this 2 by 5 moment of inertia will rotate easily. So solid sphere will rotate easily. Clear? So these are few shapes whose moment of inertia you should remember: ring, rod, disc, cylinder, and sphere. After these shapes, the next is rotational motion of a rigid, or dynamics of rotation of a rigid body. Dynamics of rotation for a rigid body. So when I say dynamics, dynamics means cause of motion. So we will study quantities responsible for rotational motion. The first quantity is torque, basically, right? So for a rigid body, you can write the expression of your torque as, the torque is I alpha. We know one more expression of torque, that is R cross F, but instead of R cross F, we will use I alpha, where I is moment of inertia, alpha is angular acceleration. Second. After torque, the next quantity is, then this tau is obviously torque. If you can remember, in translational motion, we wrote force is equal to mass into acceleration. I'm just taking analog. Instead of force, I'm taking torque. Instead of mass, I'm taking moment of inertia. Instead of acceleration, I'm taking angular acceleration. In the same way, if I write angular momentum, that's I into omega, where L is angular momentum. L is angular momentum. I is moment of inertia. Omega is angular velocity. The next thing is, after torque, angular momentum, next is work done. You can write work done as tau dot theta. Like, you know, work done is F dot S, dot product of force and displacement. Instead of F dot S, you will use tau dot theta, where tau is torque and theta is angular displacement. But this we will use for a constant torque. This expression we will use for a constant torque. If torque is constant, then your work done is tau dot theta. Like, we can use F dot S only if your work done is constant, if force is constant. In case of variable torque, you will integrate it. If you have a variable torque, then your work done comes out to be its integral of tau dot d theta. You will integrate it from some initial to final limit. After work done, you have kinetic energy. In straight line motion, kinetic energy is half mv square. But in rotation, you can write your kinetic energy is half. Instead of mass, you will use moment of inertia. Instead of velocity, you will use angular velocity. It's half I omega square. That's the expression of kinetic energy. After kinetic energy, you can use work energy theorem. Work energy theorem says work done is change in kinetic energy. It's final kinetic energy minus initial kinetic energy. So the next numericals, we will use all these 5 relations. So it's a lengthy numerical. A chord of negligible So this is the wheel. And this is connected about this axle. So you can take it like, say this is the wheel. Consider this as the wheel. This is the wheel. And I have, and a wire is wound over it in this way. A wire is wound over the wheel in this way. So if you pull this wire, then this wheel will rotate. So the entire question is on this concept. This wheel is at rest, the wire is in here. When you start pulling the wire, the wheel will rotate. So he's asking, if you pull this wire through some certain force, calculate the torque. If you pull this wire by a certain distance, maybe some 2 centimeter or 3 centimeter, then calculate the torque, work done, kinetic energy, and everything. So this is the question basically. So So the first part is very trivial. You're applying a torque force of 25 Newton to the wheel. So this is basically the axis about which the wheel is rotating. This is the radius of the wheel, and you're applying force in this way, 25 Newton, a force of 25. Okay, you people will try this numerical one by one. You're applying some force over the wheel, and the wheel is rotating about an axis. Can you tell me the formula of torque that you will use?
So torque is equal to RF sine theta.
RF sine theta, or you can use that torque is R perpendicular multiplied by F. So this is your force, this is the line of action of force, and this is your axis of rotation. The perpendicular distance between the axis of rotation and the line of action of force is R, capital R. So you can write that your R perpendicular is your capital, right? Which is 0.2 meter. Your perpendicular is equal
Yes.
to
Yes, sir.
the force which is acting on the wheel is 25 Newton. So if I substitute all values here, then your torque comes out to be 0.2 into 25. That's basically 5 Newton meter. Right. So that's your torque, which is 5 Newton meter. But you don't need torque. You need basically angular acceleration. So I need moment of inertia of wheel. I need moment of inertia of wheel. See, the moment of inertia of wheel is half the moment of inertia of disk, which is mr square. It's mr square by 2. The mass of this wheel is 20 kg. R is 0.2 square divided by 2. It gets cancelled out, that's 10. So the moment of inertia is 10 into 0.04, which is 0.4 kg meter square. So this is the moment of inertia of the system. Once you have moment of inertia, you can easily calculate angular acceleration. You know that for a rigid body, you can even write your torque as I into alpha. I is moment of inertia, alpha is the angular acceleration. So you can write that your alpha is tau by I. You can write that your alpha is tau, which is 5 by I, which is 0.4. So your alpha is 50 by 4, that's 25 by 2, which is 12.5 radian per second square. If I take part B, you need work done by the pull when 2 meters of the cord is unwound. So that's easy. You're applying a force of 25 Newton and the body is displaced by 2 meters. Means initially your cord was here. Finally, it comes here and it covers a displacement of 2 meters. So for work done, you can use this thing like work done is dot product of force and displacement. So you can write your work done as Fs cos. Can you guess the angle? Force is acting in the downwards direction and the cord is moving downwards. What's the angle between displacement and force?
0 degrees.
Yes, both the vectors are in same direction. Displacement is downwards, force is again downwards. So angle is 0 degree. So that's Fs cos 0. So work done comes out to be F is 25. Displacement is 2 meters, cos 0 is 1. So your work done comes out to be 52. Part C. Find kinetic energy of wheel at this point. Now to calculate the kinetic energy of the wheel, kinetic energy of wheel is it's half I omega square. So to calculate kinetic energy, you need angular velocity. To calculate angular velocity, you can use this relation. Omega square, so omega naught square is twice of alpha theta. See, omega you have to calculate. Omega naught, wheel was initially at rest. This was given in the question. I haven't written the statement. Omega naught is 0. You know alpha. That alpha is 12.5 radian per second square. Theta, you can calculate through this linear displacement. See, you are pulling your cord by 2 meters. So the displacement of the cord is 2 meters, linear displacement. But this due to the linear displacement of the cord, this wheel will rotate by a certain angle. So you can relate the linear displacement of the cord with the angular displacement of the wheel. So you can write your theta as it's L by R. You remember this relation, the relation between linear and angular displacement? So theta comes out to be L by R. Your L is 2 meter. The radius is 0.2. So it comes out to be 10 radian. So if I substitute all values here, then it comes out to be, this is omega square minus 0 square. It's twice of alpha theta. Your alpha is 12.5 and your theta is 10. So your omega square comes out to be, it's 250. Or you can write your omega is root over 250 radian per second. So once you have omega, you can substitute the value of omega here and moment of inertia. So your kinetic energy comes out to be half. Your I, moment of inertia, is 0.4. Then you can write your omega as root 250 square. So that's basically 250. So the kinetic energy is, it's 0.2 into 250, which comes out to be 50 joules. Okay, can you guess any other method to calculate this kinetic energy? Any other method else than calculating this omega? For kinetic energy, we can also use work energy theorem. Work energy theorem says work done is final kinetic energy minus initial. The work done we have already calculated. Work done is 50. Final kinetic energy you are supposed to calculate. Initial kinetic energy is 0. So from work energy theorem, you can get this kinetic energy directly. That kinetic energy is 50 joule. So this is how we use, you will get numericals on dynamics of rigid body. Just do one more numerical of flywheel. Remember, the moment of inertia of flywheel is that of a disk. A flywheel of mass 25 kg has a radius of 0.2 meter. What force multiplied tangential to remove that requires an angular acceleration of 25 meters. So the radius is given, which is 0.2 meter. Force is given, which is not known. Sorry. You can write your torque as F into R, or even you can write your torque as I into alpha. So you can write that your force is, it's I alpha divided by R. So your I is half mr square alpha by R. So R will cancel this square. The F comes out to be, it's mr alpha by 2. The force comes out to be, the mass is 25. The radius is 0.2. Your alpha is given 2 by 2. So it's 5 Newton. Okay, let's solve one more numerical on the same concept. The next question is, part 1. See, moment of inertia is mr square. So your m is 10 kg, your r is 0.4 square. Sorry, it's not radius, it's diameter of the ring. The radius of the ring is half of its diameter. Okay, Fazil, I'm just coming to that portion. It's 0.4 by 2. It's 0.2 meter. So if I substitute all values here, mass is 10 kg, radius is 0.2 square. So it's 10 into 0.04. It comes out to be 0.4 kg meter square. So that's the moment of inertia. After moment of inertia, you can calculate angular momentum. Angular momentum is basically I omega. But you need omega in radian per second. So you can write your omega as, it's 2100 into 2 pi by 60. So it gets cancelled out. 3, 3, 7. Okay, so that's 70 pi, I guess. 70 pi. So omega is 70 pi. So if I substitute all values, then L is 0.4 into 70 pi. So it's 28 pi basically. The third part. The third part, you need rotational kinetic energy, which is basically half I omega square. So the rotational kinetic energy is half. Your I is moment of inertia, which is 0.4. Omega is 70 pi. So it's 70 pi square. So the kinetic energy comes out to be half into 0.4 into 4900 pi square. See, pi square is 9.8. I'm rounding it off to 10. So it's half into 0.4 into 4900. It's almost 10. So it's 0.2. So this is the kinetic energy. We'll do one last numerical on this topic. This problem is in NCERT, the last numerical. The last numerical on this concept. So you have a row. So although a figure is not given, but if you want, you can draw it like this. So this is your cylinder. And the wire is wound over the cylinder in this way. So it is pulling the wire, and due to this pull, the cylinder will rotate about this axis. See, the mass of the cylinder is 3 kg. Its radius is 40 centimeter. Radius is 40 centimeter, means 0.4 meter. And the angular acceleration of cylinder is you're supposed to calculate. Force acting over it is 30 Newton. The same calculation. Huh? Tau is its R perpendicular into F, which is I alpha. So your alpha comes out to be, where R perpendicular is basically R radius of the cylinder. So alpha is its Rf over I. Your I is moment of inertia, which is its hollow cylinder, which is mr square, is equal to alpha. This R can cancel this square, so you're left with alpha is F by mr. So it comes out to be your force is 30 Newton, your M is 3 kg, the radius is 0.4. So it's 300 by 0.4, which is 25 radian per second square. The last is power. Say power is nothing but its rate of doing work. So you can write your power as the ratio of work done over time. This work done over time can be written as its tau dot omega. This is power, which is dot product of torque and angular velocity. It's tau dot omega is basically your power, tau dot omega. Now the next and the most important part of rotational dynamics of rotation of a rigid body is conservation of angular momentum. Conservation of angular momentum. See, the conservation of angular momentum says that if you have an isolated system, for an isolated system, By isolated, we mean the system where external torque is 0. If the external torque acting on the system is 0, that means the system is isolated. For an isolated system, torque is 0. That means dl over dt is 0. If dl over dt is 0, that means you can write that angular momentum is constant. So for an isolated system, the angular momentum is conserved. This is basically the law of conservation of angular momentum. L is equal to constant. But for the momentum to remain conserved, this condition should hold. Your system should be isolated. Means no external torque is acting over the system, so angular momentum will definitely remain conserved. Next, how would you use this numerical in this concept in application and in numericals? L is basically I into omega. When I'm saying that L is constant, that means the product of I into omega is constant. When I say constant, that means its value is not changing. The value of I into omega. So that I can write as I1 omega 1 is basically I2 omega 2. Its value is not changing. I1 omega 1 is equal to I2 omega 2. So if I say that I into omega is constant, that means I can even say that, just for the sake of clarity, I'm giving it a number, a constant number. I'm saying that I into omega is, let's say, 6. When I say that I into omega is 6, like if I'm saying that I into omega is constant, it doesn't mean that I is constant. I can change, omega would change, but I into omega will remain constant. When I say that I into omega is 6, that means you can put any value to I. Let's say I call I as 1. Then your omega would be 6, so that the product is 6. This product should remain constant. If I'm increasing the value of I to 2, then omega will decrease to 3, so that the product is constant. It should remain constant. I and omega can change. If I put I equal to 2, then your omega would be 3, so that the product remain constant. If I put I equal to 6, then your omega will be 1, so that your product remain constant. So when I'm saying that I into omega is constant, I'm not saying that I is not changing. I'm not saying that omega is not changing. I can change, omega can change, but I into omega will not change. It will remain constant. So that means if I'm increasing I, then omega will decrease. If I'm increasing moment of inertia, then angular velocity will decrease. If I'm decreasing moment of inertia, then angular velocity will increase. This is what we mean by I into omega is constant. If I'm increasing I, then omega will decrease. If I'm decreasing I, then omega will increase. This is what we mean by I into omega is constant. So you have plenty of applications over this concept. Almost all applications of conservation of angular momentum that you will find in NCERT is based on this factor. That if you have a system, an isolated system, somehow you decrease the moment of inertia of the system, then its angular velocity will increase. Angular velocity will increase means the rotating. It was rotating with a higher angular velocity, it will rotate fast. Now the next thing is, how would you decide that moment of inertia is decreasing or increasing? See, moment of inertia depends on size. Moment of inertia depends on size. Moment of inertia depends on various factors. One of them is size. So if size shrink, if somehow the size of your system shrink, then moment of inertia will decrease. Again, I'm not saying that it depends only over size. It even depends upon mass. It depends upon distribution of mass. But this is one factor, size, which you will use very frequently. If the mass size of your system decreases, then definitely its moment of inertia will decrease. And if its moment of inertia decrease and the system is isolated, that means angular velocity will increase. If I take some practical applications of this conservation of angular momentum, if I take first application, let's take the rotation of Earth. Say when Earth is rotating, it's basically an isolated system. No torque is acting over the Earth during rotation. For rotation, Earth is an isolated system. Means no external torque is acting over it. So if Earth shrink, can you guess what will happen with its moment of inertia with Earth shrinks? For collapse, what will happen with its moment of inertia? It will increase or decrease?
Decrease.
Yes. If it shrink, then moment of inertia will decrease. If moment of inertia decrease, then what will happen with angular velocity?
It will increase.
Yes, angular velocity will increase. I mean, it will start rotating fast. Okay, if it starts rotating fast, can you guess what will happen with its time period? Yes, Fazil.
Decrease.
Yes, time period will decrease. So instead of 24 hours, it may be possible it cover rotation in 12 hours. Time period of rotation will decrease. Time period of rotation will decrease. So this will happen if Earth shrinks. This usually happens in stars. When stars consume all their masses, then it starts shrinking. When a star shrink, then its angular velocity increases, starts rotating at a very fast pace. Just note it down. We'll do few more examples, few more applications of conservation of angular momentum. But remember, in all applications, these steps are common. Either the size of the system will decrease. If the size is decreased, then angular velocity will increase. Or the size will increase, eventually angular velocity will decrease. So in all applications, these steps are common. Moment of inertia will change and angular velocity will follow. There's one more application given in NCERT. Oh, can I do one thing? You all have NCERT?
Yes, sir, we have.
So instead of writing everything, I'm just mentioning the topic and I'm giving you details, but I'm not dictating anything. The detail you will write yourself, okay? So the first is, if Earth shrinks, then moment of inertia will increase. These are applications of conservation of angular momentum. These are applications of conservation of angular momentum. Applications of conservation of angular momentum. In all applications, the steps are same. Size will change, moment of inertia will change, and angular velocity will change. So the first was of Earth. This is the second example, the second application. Case of a dancer. Say if you have a dancer is rotating, this is the dancer. He is rotating and his arms are open. He is rotating about this axis which is passing through the center. While rotating, if this dancer fold his hands, while rotating, if he fold his hands. Now, can you guess what will happen with the moment of inertia?
Will decrease.
So when dancer, if initially the moment of inertia is I1, finally the moment of inertia is I2. On folding hands, moment of inertia decreases. And angular velocity increases. So it will start rotating at a faster pace. As soon as the moment of this dancer fold his hands, his moment of inertia decrease and his angular velocity will increase. So this is the case of dancer. Just like dancer, you can have many more cases where you will see very clearly that moment of inertia is changing, the angular velocity will follow inversely. If moment of inertia is decreasing like this example, then angular velocity will increase. And the third case is if ice caps on poles of Earth melt, then so if ice caps means on the North Pole and the South Pole, if all glaciers melt, can you decide what will happen with the moment of inertia?
It will increase.
Because the water will spread throughout the surface of Earth, its moment of inertia increases. The moment of inertia of Earth increases. So if moment of inertia of Earth increases, then what will happen with the angular velocity?
It will decrease.
Decrease.
So angular velocity of rotation decreases. Because if ice caps melts, then all ice will get converted into water and that water will spread uniformly over the surface of the Earth. So if the mass distribution is uniform, then moment of inertia will decrease. Sorry, it will increase. Because the separation from the axis of Earth will increase. If someone have an issue that why the moment of inertia will increase, see this is initial. Initially, this is the ice cap. The whole ice is in this region only. But once this ice melt, then the water gets distributed throughout the surface of Earth. See, earlier the separation was small from the axis, but now the separation is large. And moment of inertia is mr square. It depends upon the separation from the axis. That's why if the ice caps, all the ice on the North Pole and the South Pole melts, then due to the distribution of mass, moment of inertia will increase. And eventually the angular velocity of rotation will decrease. So the next question is, what will be the duration of day say if Earth shrink to 1/64 of its original volume, that means the radius of Earth will shrink, its moment of inertia will decrease, then we'll see how its time period will change. Normally the time period of rotation of Earth is 24 hours. You will see how this time period will change due to shrinking of Earth. So first of all, I need relation between the initial volume and the final volume. So the final volume of Earth is, as per question, is 1/64 of initial volume. Earth is shrinking. So I'm writing the final volume by 2 and initial volume by 1. This is given in question that final volume is 1/64 of initial volume. This will give you a relation between the initial radius of the Earth and the final radius of Earth. Volume can be written as it's 4/3 pi r2 cube 1/64 into 4/3 pi r1 cube. 4/3 pi will cancel this 4/3 pi. R2 cube by R1 cube will be 1/16. Sorry, not 16, 64. So if I take cube roots on both the sides, you will be left with R2 by R1 is 1/4. So that's the relation between R2 and R1. I call this as equation number 1. Since no external torque is acting on the earth, so you can write that your I1 omega 1 is equal to I2 omega 2. So I1, earth is a solid sphere. So the moment of inertia of earth is, it's 2 by 5 mr1 square omega 1. I2, it's 2 by 5. Mass is not changing. Only the radius is changing. So it's R2 square omega 2. 2 by 5m will cancel this 2 by 5m. You can write your omega 1 as 2 pi over T1. You can also write your omega 2 as 2 pi over T2. So if I substitute all values here, this is R1 square multiplied by 2 pi by T1, R2 square multiplied by 2 pi by T2. So this 2 pi will cancel this 2 pi. You are left with R1 square by R2 square. It's T1 by T. So you know that R2 by R1 is 1 by 4. That means R1 by R2 will be 4 by 1. It's 4 by 1 square is T1 by T2. So it comes out to be 16 is T1 by T2. So your T1 is 24 by T2. Your T2, the time period will comes out to be, so T1 is 24 hours. This is the time period of rotation of Earth. It comes out to be 24 by 16. It comes out to be 6 by 4, which is 3 by 2, which is 1.5. So if Earth somehow shrink to 1 by 64 of its original volume, then the duration of the day is 1.5 hours. Is it clear?
Yes, it's clear.
Yes, sir.
This is how you solve problems on moment of inertia. Initially, the data would be given, most probably moment of inertia would be given. You have to calculate the final thing.